that you remember this problem. I want to go from here along this thing. I have this given height, and I have a mass that is sliding over the surface. And what's the shape of that surface? Y as a function of x. That results in this sliding in minimum time, right? What we call the Brewster-Chrome problem. So in this era, looking for optimum shapes was evolving. He didn't formulate the calculus operation. There is no calculus operations yet. There are problems that optimizing some scale cost. Here is the time of the excursion, and we're looking for function, for shapes. Okay. So Aubertouille, French scientist, as the name may clearly tell, 1678, this work. This was a paper by Johann Bernoulli. 1678, Aubertouille. Now this is mature a little bit. So Aubertouille said, you know what? The motion, he was bold enough to state it. The motion, every single motion. You have a particle and throw it, the vibration of the tree leaf, the motion of any object, the motion of a planetary, say, orbit, or a planet in its orbit, any motion of any object in the entire world is such that a certain magic quantity is minimized. He's basically saying that nature is not doing things haphazard. It's not doing things without optimization. Nature must be doing things in an optimal way. So every single motion occurs such that a certain magic quantity is minimized. There is an optimization behind it. Motion is such that a certain magic quantity is minimized, and he proposed that this magic quantity is Leibniz-Frisbeeber thing. So he said every single motion is such that the following integral 2t, the integral of the Frisbeeber, the integral of the kinetic energy is minimized along the motion. You want to move from here to there. This is the Q space. Okay? You want to move from here to there. How you move in the configuration space, there is no time now. How you move in the configuration space, how you connect these 2 points in the configuration space, when you throw a particle from here to this point, how you connect this trajectory in the Q space without any regard to time, is just the function that minimizes this integral. Every single motion in the world. He called this integral as the action integral. It's a hypothesis like this is a hypothesis like. So everything in dynamics is a hypothesis. He was not a great mathematician, so of course he could not proceed. This is not complete yet. We can know why. But you can see that he is the originator of this thing. We're going to continue now. And I'm going to say, okay, here, 17 now. I guess 07, this is Euler, a great mathematician. When it comes to mathematician, then problems will be solved. 1736, Lagrange. Another great mathematician, if not even better. So, first of all, they said something, they observed something very important. What's that? That here we are talking about the Q space, the configuration space. So you're basically, okay, I will assume that I know the mathematics, the required mathematics. Assume that I know it to solve this problem. solve this problem by, minimize this integral, find this q, find this shape in the q space, find this trajectory in the q space that minimizes this integral. Assume that I know. So your solution now gives me this trajectory in the q space, no regard whatsoever to time, no regard whatsoever to how this motion will occur versus time. So the time is removed, has to be removed. Okay. So Euler said that if the time has to be removed, then we need an equation to remove the time. So he proposed the following formulation. Simultaneously with Lagrange, they both agreed on that. That the motion is such that the action integral is minimized. Minimize this functionally. Right? The action integral is minimized subject to a constraint to remove the time dependency. This constraint obviously is the conservation of energy. U is constant, or your initial energy. Okay? If time permits, I can show you how we can remove the time from this equation, but it's just a little bit technical. We have equation, we can use this equation to get any variable we like. So we can use this equation in particular to get the time dependency. And then substitute it here, or treat it as a constraint optimization problem. We're minimizing the functional subject to a constraint. This is all what we're doing here. So actually, when Euler encountered this problem several times, together with Lagrange, they created a calculus. So Lagrange in particular, he said, well, whenever we're solving a dynamics problem, they were not solving it using f equals ma like we do nowadays. Whenever they solve a dynamics problem, they have to go and do the thing that we did last time. When we derive the first order necessary condition, they do the integration by parts and take the derivative with respect to epsilon and all this kind of stuff. So if we're doing every single problem, let's create a calculus for it. Let's create a routine for it. And this routine became the calculus operation. Is that now we have just readily equations that we can apply. Lagrange created the calculus operation. So let's create a calculus for this thing. Now this problem is simply a typical calculus operations problem. Minimize a functional subject to a constraint. Euler, he proposed or developed in the process the isoperimetric problems. Lagrange developed the calculus operation as a whole. Actually, Hamilton, who will come next, he used to call Lagrange as Shakespeare of mathematics. You can see now what world we're living in now. So this principle is called, as you see, this is the action integral. We're minimizing the action integral. So this principle is called the principle of least action. Is that the motion of every single thing, if I just drop this guy, its motion is such that the action integral is minimized. Okay? It's a very bold thing and very intriguing, and it holds at whatsoever level. Newtonian mechanics is only valid within the size, the length scale, and the mass scale that we live in. Okay? If you go very large length scales, Newtonian mechanics fail. If you go very small length scale, Newtonian mechanics also fail. But this principle of least action works all the way. In particular, it gives you exactly Newtonian equations in the world that we live in, that we're going to see in a minute. Probably you can imagine now. If you go very large scale, then you have relativistic mechanics of Einstein. This is nothing but the principle of least action. If you go very small scale, this is quantum mechanics, and this is nothing but the principle of least action. So every single motion in this world happens such that the action integral is minimized. Again, if time permits, I can show you how from here we can get to the next step. It's straightforward. But, as you can see here, that's still valid only for conservative motions. because it uses, in particular, it uses T plus VA for constant in the formulation. We have to satisfy this constraint. This was the main difference, if you can see here, the main difference between Euler-Lagrange formulation and Mugur-Twee, which is actually people didn't pay any attention to him and didn't give him credit because he didn't finish the problem. It was actually a philosophical principle than anything else for him. He's saying nature must be optimizing things. The main difference between this guy and that guy is the addition of that constraint, because this problem without that constraint will not give you any correct result. Adding that constraint and treating it in a special way, you can get all the equations of motion that we're dealing with in this course. But still, it requires conservation of energy. So here is the next step. It's Hamilton. 1805, 1865. In 1834, he published this paper. The principle of least action in its current format that we know nowadays. But you can see that the originator of the principle of least action was Mugur-Twee. Here is the action integral. It's simply the integral of L, the Lagrangian function, which can be function of time. I don't care about conservation of energy. And of course, it's function of q's and q dots. dt, and we're not talking about the q space, we are talking about the qt space. So give me t naught, q naught,